Go ahead then with,
All right.
get started. Thank you for attending. My name is Sammy Pearson. I'm the director of the Coos Bay Public Library. And with great pleasure, we have Dr. Aaron Coyner here tonight, who is going to discuss the James Webb Space Telescope.
Thank you, Sammy, for the introduction. And yes, we will talk a little bit about the James Webb Space Telescope, a telescope mission about a decade and a half in the making, just in terms of getting all the parts right, and that is scheduled to launch from our pale blue dot of a planet on, I believe, December 22nd now. It was originally scheduled for December 18th. It's been pushed back to the 22nd, and depending on weather at the launch sites and various other things, there's about a month window for it to launch this time before they'd have to reschedule it again. We're hopeful that by the end of this month, it will be launched and headed toward an orbit around Lagrange point L2. I'll talk a little bit about where that is and why that's important for an object like this. And we'll talk a little bit about what James Webb is scheduled to do, sort of not replacing Hubble, because we can't replace our dear friend, but we do our best to sort of extend and look beyond what Hubble was able to do and focus on some new and interesting territory in astronomy. From looking as far back into the past as we can with Webb's cameras will allow us to look back at the very early days of the universe because of redshifting and other things of the light sources. Most of those sources are actually now in the near to mid infrared, which is where James Webb Space Telescope focuses most of its observing. We'll also have a way to look into supermassive black holes in the centers of galaxies, and look at exoplanets around stars as they're forming and as they've existed. We'll have new resolution to learn more about exoplanets. We'll also be able to discuss a little bit more about the exoplanet atmospheres. I am giving this talk as not only the physics, engineering, and astronomy professor at Southwestern Oregon Community College, more on that later, but as one of NASA's JPL Solar System ambassadors, which means many of the slides that you see in this talk are actually from direct from NASA training that I actually sat through with, and I leading up to this mission launch at the end of the month, to discuss what exactly Webb can do. So when we get to slides that aren't mine originally, you'll see the names of the actual scientists and the mission specialists that are involved. I am using their work with permission because they tell us we can use all of the training materials, and it helps to put the talk together, having slides that explain what you're actually trying to explain without you having to make stuff up. I'm fairly good at making stuff up, but I'm not going to try to today. So with that being said, what do you do when you have to replace a legend? So, or at least if you're not replacing a legend, you're at least trying to follow a legend in the sense of following Hubble. If I can get there we go. Helps if I hit the right button and it behaves. So this is, as they're constructing part of the primary mirror for the James Webb Space Telescope. We'll talk a little bit about how the mirror comes together a little later. JWST was expected to be Hubble's successor, and it was supposed to be launched years ago. But Hubble, after they'd had the several missions and the several maintenance missions to correct its vision problems at the beginning, once we got the stunning pictures from Hubble that we have gotten used to over the last 30 years, the last 3 decades, that we have enjoyed Hubble images, there's always come to be a point when there would be a replacement for Hubble, and there would be a replacement based on observations and based on new findings in astronomy that would help us. JWST is forever linked to Hubble because it's always viewed kind of as Hubble's successor, but it will look at completely different, mostly different things. There are some things that Hubble touched on, but because of the wavelengths that Hubble looked at, it wasn't able to really go as deep with it. But I find this amusing. You always know it's entertaining when the engineers that build the telescope are trying to promote how well the mission will go, and their exact wording is the Webb telescope will fundamentally alter the understanding of the universe. And I'm sitting here going, having been through several things where people have said that this will be a complete game changer. I'm like, okay, no pressure. I've seen enough of these NASA missions that they are very good and they do come up with lots of things, but there are always things that we don't expect. So when you're going in with the hype of this will fundamentally alter our understanding of the universe, it's kind of a no pressure moment. But when we talk about what all it's expected to do, it's very much accurate of what they're attempting to do with it. So Webb, it's a space telescope primarily observing in the near and mid infrared. So it's essentially looking for heat signatures, although more specifically, it's in the infrared spectrum. So it would be things that we would see in like night vision goggles, and then further down in the infrared spectrum. It is tested to be 100 times more powerful in terms of observational resolution than Hubble. And observations in the infrared are key for a number of different reasons. We can look at galactic origins. We can look at how galaxies evolve over time. And how do they interact when they collide? We'll talk a little bit more about that as well. We can look at individual star and planet formations of different planetary systems. We can look at the exoplanets. We can actually get direct observational evidence of planets roughly the size of Neptune. Currently trying to get observational evidence of exoplanets, they pretty much have to be the size of Jupiter or larger to be able to do it from the ground, or to be able to do it from Hubble. But with Webb, we should be able to improve that sensitivity to where we can actually find what are called super Neptunes, which are exoplanets about the size of Neptune, slightly larger, but decidedly smaller than the mass of Jupiter. So we're looking at much smaller exoplanets that we may be able to determine from the exoplanet observations whether they're in the habitable zone of their stars based on analysis of the spectra that we get, because we can actually view some of the light through the atmospheres of those planets. So if they have atmospheres and they're close enough to their star, we can determine if there's something that would be habitable similar to our own planet, or something at least akin to it. We never really know what to expect in terms of habitability, just because for us to presume that all planets will evolve like ours to support basically beings that we're used to with the same types of atmosphere is kind of putting kind of an egocentric spin on the universe. And yes, we tend to do that, but we probably shouldn't. We'll also look at the growth of supermassive black holes, and I had to stop myself from putting the Muse song in the background while doing this one. But but the growth of supermassive black holes through galactic collisions, because we know that major galaxies and our typical regular spiral galaxies like ourselves, the Milky Way and Andromeda, as well as numerous other galaxies, are all believed to have supermassive black holes in the center. And largely it's believed that the supermassive black hole is essentially being fed by the galaxy itself. But the theory involved here is that as galaxies collide, because they do, space is vast, but it's not completely infinite. There are occasional pileups and traffic jams and occasional times when things hit each other. And even on large scales, when you have giant galaxies, you have other giant galaxies that can pass through and get gravitationally distorted, and sometimes they can merge. But as they merge, the black holes merge too, and they can actually grow in size. We'll talk more about that as we go. And then, as I said, the last piece is essentially looking back as one of the biggest historical missions in all of astronomy, in the sense that we can now look very far back into the early sort of primordial universe, about 13.5 billion years ago, and start to see some of the older objects in the universe whose light has been redshifted because they're so far away, to the fact that they're brightest in the mid-infrared. So how are we going to do this? Well, Webb has 4 scientific instruments. There's the Nir Cam, which is the near infrared camera that was designed and built by the University of Arizona and a team of NASA scientists that were also funded with it. So Nir Cam actually looks at kind of and I'll get into some more detail on that, but it does primarily shortwave and then long wave wide field deep imaging. So you're looking at essentially what Hubble Deep Field was, but in the infrared, and we can use it for kind of longer exposure times to take deep images of particular areas of space and essentially determine new objects and have new objects pop in, because you have essentially more light gathering capability the longer the exposure time is. The second instrument is called the Nir Spec, and that's from the European Space Agency. It does mid-infrared imaging from 5 microns to 27 microns, and does spectroscopy from about 5 microns to about 29 microns. And you're looking at spectroscopy because every element has its own spectrum. And if you're looking at things in terms of, say, looking for, say, hydrogen, or looking for carbon or oxygen, each one of those elements will have its own spectrum and will have its own set of lines that it produces in its spectrum. And we can look with a spectrometer like the Nir Spec that will allow us to detect those particular line signatures that would indicate this is a carbon atom, or this is a collection of carbon atoms, or this particular atmosphere has a lot of carbon monoxide in it, or this particular atmosphere has a significant amount of oxygen or nitrogen or whatever else we happen to be looking for at that time. We can actually look for signatures that would lead to that. Our other images at the beginning, at the front of the instrument panel is the mid-infrared instrument, again, provided by the ESA. There was some component collaboration with NASA Goddard Space Flight Center. That actually operates in the mid-infrared, which is about the 5 microns to 29 micron range that we were talking about. are we are the, and the last one is from our friends at the Canadian Space Agency. It's the fine guidance system, but it also has a near infrared imager and a slitless spectrometer with it. We didn't have a cool nickname for it, so it's just the FGS and then the nearest system. It does do fine guidance of the telescope. It also does near infrared imaging from 0.8 microns to 5 microns. And we're looking at essentially 2 arc minutes by 3 arc minutes in size. And then if we can see to a redshift of about 700, or a resolution of about 700 if we have a chronograph in there. So these are our instruments, Nir Cam, Nir Spec, and the nearest instrument are all near infrared, which is from about 0.6 microns down to 5 microns. Our mid infrared imaging system goes from about 5 microns to about 27, and then our spectroscopy goes to about 29. So our sort of deeper infrared will come from the MIRI instrument, but the other 3 will give us sort of near infrared, which is a typical infrared range that we would see for like night vision goggles and things. So as I said previously, some of these slides I do borrow from I do borrow from experts. This was from Susan Neff, who's a deputy project scientist for operations for JWST, and she currently works at NASA Goddard Space Flight. And in this case, we're talking about how the spacecraft is about ready. You can kind of look at, this is a comparison of the mirror and looking at sort of the detectable spectrum. You have basically our standard mirror. The person standing there is basically what can we find in terms of this is a person by standard. We're expecting a person is about 1.5 meters tall. So this is by person height. Hubble's mirror is a little over 2 meters. It's about 2.5 meters in diameter. And Hubble did a little bit of observation in the visible light, and then got a little bit into sort of the near infrared and kind of the baseline of visible. We have the Herschel instrument, which is actually a long infrared and radio instrument that has basically a mirror that is approximately 3.5 meters in diameter. And then James Webb, you've got the honeycomb mirrors, which you'll see a lot of when we get into the actual visuals, that give us an actual mirror diameter when it fuses together and it works as one single mirror of about a mirror diameter of about 6.5 meters, or about 4 people tall. So the mirror diameter for the instrument is about 4 meters. Mirror diameter is huge for telescopes because the bigger the mirror is, the more light you can collect. The more light you can collect, the more you can resolve things. The more you can resolve things, the more stuff you can see. So essentially, by almost tripling the diameter of the mirror, you actually increase the light gathering capability compared to Hubble of about 7 times. And you still have Hubble-like angular resolution in the near infrared, but because you have 7 times the light capability, you have the same resolution, but now you can see a lot more stuff. And if you do observational capabilities spanning optical and mid-infrared spectrum, you can do essentially an image with just say 1,000 seconds per band, and this is the simulated JWST, and you can see that the image is much clearer. This is a Spitzer image from the Spitzer infrared telescope, which was the prior infrared telescope that had gone up, and this is 25 hours per band. So 1,000 seconds is roughly, well, 600 seconds is 10 minutes, so 1,000 seconds is about 17 minutes. So this is about 17 minutes of exposure time, and you can see how clear this image is. This is, of course, simulated because we haven't actually sent the thing into space yet to be able to take images, but this is what we expect JWST to do. This is that same field, but with Spitzer, that's 25 hours of exposure time per band. So what JWST can do in 17 minutes dwarfs what the Spitzer Space Telescope could do with an entire day. So that's what we're hoping for. So in order to in order to figure this out, we actually had to solve two key problems. We had to get a primary mirror that is larger in diameter than available rocket fairings. So how do we build a mirror that is bigger than the rocket that can carry it? And then we had to achieve high stability cryogenic at about 40 Kelvin, which is about minus 233 Celsius or minus 388 Fahrenheit for an operating temperature. Those operating temperatures are not hard to get in terms of in the vacuum of space. You can get that cold, but getting that cold and stabilizing it to where it would remain that cold is a bit of a trick. So this is our launch vehicle. It's called the Ariane 5. And you'll see that the spacecraft kind of folds up, and we have all of these individual little, all of the little hexagonal or the little hexagonal pieces that become part of the large mirror. They all fold up into the actual launch vehicle. When the launch vehicle allows Webb to be deployed, it's deployed kind of on this platform ship that is essentially the solar array and the spacecraft bus, and then the telescope is actually mounted on top, and you have the large primary mirror, which is all of these hexagonal pieces kind of fused together into essentially a honeycomb mirror, and then it reflects off the primary and bounces through a secondary mirror, where it then reaches into the center of the honeycomb mirror, which is where all of the instrumentation lies, and then ties into the central bus. I'm going to go back to talk a little bit about one thing. Hubble, when it was up, it actually stayed in fairly low Earth orbit, about 570 kilometers above the surface of the Earth. It stayed in Earth orbit and stayed, and it just stayed in orbit for 30 years. That made it possible for us to send a spacecraft or send the space shuttle up to fix it a couple times. Because you can actually do that in low Earth orbit, because you can have other spacecraft go up there, and then you can still manage to come down. Webb, we're going to do something completely different. We're actually going to put it out in orbit around what's called L2, which is the which is the Lagrange point. A Lagrange point is the point in any gravitational system where the gravitational forces actually balance, and you actually have a stable point that something that is at the Lagrange point becomes essentially fixed. There are 5 Lagrange points at any given on any given two-body system, including our Earth-Moon system, and one of them, L2, is out well on the far side of the on essentially the far side of the moon. So we're 1.5 million kilometers from the surface of the Earth. So we're about 4 times the orbit of the moon out to where Webb is actually going to be observing things from. And it's going to basically do a halo orbit around the Lagrange point, because the Lagrange point is fixed and it allows it to just orbit around that point for gravitational stability. Now, I don't talk fast enough for some of these slides, but this is sort of a simplified timeline. This is from, again, from our friends at Goddard. We're looking at, after launch, it takes about 20 days to fully deploy the Webb Space Telescope, and it finally reaches orbit about 25 days in. It has to cool for about 15 days, and about day 40 is when we get to turn the near infrared camera on. And then about day 50 is when we get images from all 18 of the mirrors. About day 60 is when we get everything aligned to the near Earth camera. And then we start aligning all of the other instruments. And then by about day 100, MIRI is at its operating temperature. In day 120, about 4 months into the mission, the telescope is finally aligned. And then we start cooling and commissioning all of the instruments. And about 6 months after all of this is done, we have all the instruments ready, and then we can start with the cycle 1, which is when proposals for astronomers to ask for particular observations of particular areas can start. So we launched this in December. The first light images you'll probably see or hear about will come out around June or the first part of July. And the first actual observations that are strategic observations that are made with James Webb will start sort of mid-summer of next year. And I think the mission is technically listed for like 5 years, but I'll remind you that Hubble was technically a 5-year mission too, and it lasted for 30. So I would count on Webb, at least in some capacity, extending well beyond that. So so that's how we get everything set up for how Webb works. I do want to spend the next little while on the slides talking about what exactly Webb can do. And for that, I will borrow from another training. This was from Dr. Nestor Espinoza. He's with the Space Telescope Science Institute, which are the scientists and people behind Hubble. But he's also working on, okay, what can Webb do now that Hubble couldn't? And one of the things that has become sort of a key point for all of astronomy in the last 25 years, to the point where last year the Nobel Prize in Astronomy went to the 2 scientists that were responsible for the discovery of the first exoplanet, is now in the last 25 years, we found that it's statistically more probable for a star to have planets than not to have planets. So now that we know that there are that many planets out there, we'd like to know more about them. And Webb is actually going to give us a little bit more of a window into the exoplanets than other craft such as Kepler and TESS have been able to do. So our hope is that there will be planetary systems that we can actually have a wide field of view that's about 20 astronomical units, and we can actually physically observe and essentially individually would resolve the planets. So you can see that there's an exoplanet B, C, and D here on the image on the left hand side correspond to the three different correspond to three different planets around this star in the center that's been blocked out by, it's essentially been blocked out by an occulting disk because we don't want the starlight to blind essentially to blind out any potential planets that are there. If we can't directly resolve things, we can actually look at essentially what happens in terms of transiting exoplanets where we have light that comes from the star. And then if one of the planets passes in front of the star, the light that we get from that star dips for a while because essentially the planet is doing a partial eclipse. So the light dips for a while, and then based on how long this eclipse lasts, we can determine a little more about the size of the planet and the size of the star itself. And then at various points, you have both the planet light and the starlight. And then later on, you might have you'd have a lower dip where essentially now the planet goes behind the star. So now you don't have the planet light because the star is blocking it all out. And so you can see where these, based on where these fluctuations are in the overall spectrum, we can actually find transiting exoplanets, which is how we've discovered many of the exoplanets that we have now. That's how Kepler discovered most of theirs, and then TESS, which is our current exoplanet hunter. Literally, the acronym TESS stands for Transiting Exoplanet Survey Satellite. So we use it to find transiting exoplanets. Direct imaging, the bigger the planet, the harder it is to find. Or the bigger the planet, the easier it is to find. The smaller it is, it becomes really hard to find the small planets because essentially the starlight will blind everything and you can't really detect it. It feels more like it's almost within the noise of the starlight spectrum. So it's really hard to locate the smaller planets. And so we're looking at planets. These are on scales of Jupiter mass. So things that are 10 to 100 times the size of Jupiter, 100 times the mass of Jupiter, you can actually find those fairly easily because they're fairly big. They have a decent gravitational field. They're also usually much easier to see because if they do transit, they cause enough of an eclipse that you can actually see a difference. If they don't transit and they're out where you can find them, they're actually large enough that you can resolve them normally. What we want to find, though, is we want to find things that are closer to the size of Earth. So we want to find things that are kind of down in the harder corner. Because we as Earthlings don't like to do things easily. We exist on a planet that's really hard to find. So right now, the best we can do from Earth is sort of this range of what is detectable, and it's slightly the size. Basically, we're looking at things that are close into the star. If we're inside of 10 astronomical units, we need to find things that are about 5 times the mass of Jupiter. Outside of the star, the further out you get, when you get to 10 or 100 or 1,000 times an astronomical unit, and for those who haven't had an astronomy class in a while, an astronomical unit is the average distance of the Earth's orbit. So the distance from the sun to the Earth's orbital plane is 1 astronomical unit. So when we talk about 100 astronomical units, we're talking about planets that are 100 times further out from their star than Earth is from our sun. And 1,000 astronomical units is to give you kind of a baseline. the edge of our solar system at Pluto is about 40 astronomical units out. So that gives you kind of a scale of our own system. Jupiter's at 5, Neptune's at about 30, and then Pluto would be out at about 40. So the best we can do from Earth is to locate things that are bigger than Jupiter and closer in. When we add in the James Webb Space Telescope, we can actually get down to where we can find Neptune-sized planets or about Neptune-sized planets out 100 to 1,000 astronomical units out from their star, and inside of about 30 astronomical units, we can get down to something about the size of Jupiter. We believe that there are many exoplanets that fit into this regime in what are called super Neptunes. Those are slightly larger than Neptune and much further out from their star, because when we're dealing with larger stars, they have much larger solar system or much larger planetary disks that can extend several astronomical units and even thousands of astronomical units out. Sammy, you know me by now. If I start talking too long, feel free to either pull the plug or hit the mute button. One of the things that we're allowed to, one of the things that is important to look at in terms of what can we resolve from an exoplanet perspective is we have, if we have direct imaging, again, we can see all these. I skipped one too many slides. But when we're looking at what wavelengths we're able to do, the sun generally, most of the sun's energy is in X-rays and infrared, although it does peak in the green, kind of in the visible spectrum. If we're looking at things from a perspective of something in the infrared, we can actually see some light from, say, a furnace that would typically peak kind of in the near to mid infrared, and then something like the Earth as a planet is at about 300K. But it would actually start to show emission about halfway through the JWST bandwidth. So having those near infrared and mid infrared cameras actually allows us to detect signals from planets that are radiating at similar temperatures to our own. And so as we're looking in basically the near and the far infrared, we get different images. And here's an idea. Here's kind of a plan of how this works. If we're doing this from an optical camera, you can kind of see that so the stove being off, we basically just see the black rings of the stove. The stove being on, we see it starts to glow a little bit red because we can see some of the visible light. But if we look at it through an infrared camera, when it's off, we still have kind of a nebulous infrared signature because there's still some heat there. And then the minute it turns on, it becomes really, really bright. So within the infrared, most of the heat that your stove is producing is going to come out in the infrared. Our stars, we've talked about basically being a giant furnace before. So if we have basically a giant furnace in the form of a star or a planet, that will also produce a large signal in the infrared. So having cameras that look in that give us an opportunity to see more signals and more direct evidence of the planets as they exist. So how are we going to find exoplanets? When we talk about sort of transiting exoplanets, I talked a little bit about how transits work, but if we have transits, we can actually find more information in terms of what are we learning. And so the idea is that James Webb will actually allow us to discover down to like Neptune mass exoplanets far away from their stars. And so when we find smaller planets than Neptune, we can actually find the transiting exoplanets that are actually smaller than that, because we'll be able to do it with more resolution than before. So here's an example. When something passes through, if it has an atmosphere, when we go through it and we get observations from it, the atoms and molecules actually radiate in different colors. So when transiting or essentially when we look at the transiting exoplanets going across, they actually have different colors that they radiate in, and we can actually learn more about the specifics of what we're looking at. And let's look at this is a spectrum. If we've got a transiting exoplanet that's moving in wavelength, essentially the purple wavelength is hydrogen, the yellow or the green and the yellow are kind of in sodium, and then the red, you've got the potassium line there. And you can actually see that at these various points, you can find these are areas where the exoplanet size will vary. So if you get a large sodium spike and a large potassium spike, then you ended up with a much larger exoplanet. And one of the reasons for wanting to do this is actually the case of TRAPPIST-1, which is a system that was discovered a few years ago. It's a system of basically a red dwarf star that has 7 orbiting planets, 5 of which are believed to be either in the temperate zone or in the habitable zone of the star. And we were able to see some of the stuff with TRAPPIST-1. So spectrum from essentially TRAPPIST-1c, we're seeing things like carbon dioxide. TRAPPIST-1e, we also see a lot of carbon dioxide spikes. We see some water. We see other organic compounds that would lead to our ability to support life. And based on where we are, given a red dwarf star, these C and E in particular are believed to be either in the temperate or in the habitable zone. So they're not to the point where they're frozen out like TRAPPIST-H would be, but there is a possibility that there would be essentially temperate opportunities for life to exist in the sense that there would be some there. Now, there's a lot of individual factors as to whether that would happen, depending on magnetic fields, orbital rates and spin rates of the planet. I mean, Venus is basically the same size as Earth and not too much further from the sun. So it's technically on the edge of the habitable zone, but because of a runaway greenhouse effect, it's 900 degrees and it rains sulfuric acid. So it's like, no, thank you. So after the exoplanets, one of the other things is, how do you grow a supermassive black hole? And the best answer that we have, and this is from Dr. Vivian Yu of the University of California, Irvine. And one of the ways you grow a supermassive black hole is you take 2 spiral galaxies or 2 barred spiral galaxies and you smash them together. So this is kind of an example of black holes. Some of this is visual. Some of this is movie based, and some of this is actual data. So this is kind of a Wikipedia Commons image of what we expect basically an artistic rendering of a black hole. You have the black hole. You have essentially what's called the event horizon, and anything on the outside of it becomes what's known as the accretion disk. And things don't technically get sucked in, but they end up radiating as they're falling into it. It's not actually sucking them in, but it's more but it's more they're just gravitationally falling into a gravitational well, and they get sped up to the point where now the light shifts out to where they can't, to where the light goes away. Gargantua is actually from the movie Interstellar, which is a great movie that everybody should go see. Not necessarily after this talk, but at some point you should go see it. The M87 black hole, this is an actual image. This is from the Event Horizon Telescope collaboration, and I always refer to this as the astronomical equivalent of the Eye of Sauron, because I can't see it any other way after I saw the picture the first time. And then this is sort of a gravity or a artist conception of, you have a black hole in the center, and as it accretes things and as it starts to have things fall into it, you actually get jets and you get magnetic field lines that come out of either end of the black hole. So you end up getting jets of what are called Hawking radiation that come out of the black hole due to it accreting. So we have some fun things when we talk about mass ranges for compact objects and for and the plain ones, anything that's about the mass of the sun, you get things that are knocked down to about the size of a white dwarf. They get dropped down, or they end up falling to about the size of a planet, but they're not really, but they don't do anything really interesting. They're just kind of they slow. These are where good stars go to die. Our sun will eventually become a white dwarf, and then will eventually just burn itself out, but it's not going to do anything too catastrophic because it's not big enough. Then you have the fun one where the core is between like 1 and 3, which is a neutron star. And neutron stars are a mess, my best stat for neutron stars is, okay, take a star the size of the sun and collapse it to the size of Portland. There you go. That's what a neutron star would look like. The other interesting fact of the day with neutron stars, the density of neutron stars would be essentially equivalent to taking every car and truck in the United States of America and simultaneously crushing it into a 1-inch cube. I will allow you to go get duct tape so your head doesn't explode any further. But neutron stars are interesting, but then once you get past neutron stars, then you get to things like stellar mass black holes that are typically 5 to 10 times the mass of the sun to start with, and then they can get bigger. They can go up to about 100 times stellar mass, about 100 stellar masses. This is kind of challenged at the moment because there is a little bit in black hole theory that indicates that beyond about 100 solar masses, that a black hole cannot really exist because of essentially pair-creation energy. But recent observations from LIGO, we had Dr. Ray Fry from the University of Oregon speak to us at SWAC last month. That talk is available online through the SWAC live stream, but they were talking about recent observations that they had made where they had measured black hole mergers based on gravitational waves, and they actually found a couple that actually fit within this intermediate sized black hole question mark that theoretically should not exist, but they're actually showing evidence of it. And then when you get up to 1 million times the size of the sun, then you get these supermassive black holes that are in the center of almost every galaxy. So how does a black hole get to be that big? And so the bigger the star system, so if I have a globular cluster, I end up with a black hole. That globular cluster M15 has a black hole that's about 1 million solar masses. Globular cluster G1 has one that's about 10 million solar masses. And you start to get to galactic star bulges and you get to larger galactic stars, you can actually get up to where your stellar mass of the system. So the stellar mass of the entire system is roughly, say, 1 trillion solar masses, and the stellar mass of the black hole becomes about 1 billion. So for globular cluster M15, there's about 1 million solar masses worth of star there, and there's about, say, 10,000 solar masses that's the black hole in the center of it. And as things get bigger, so do these supermassive black holes. And so this is kind of the idea, is as we look at essentially early stage mergers, late stage mergers, and then looking at post merger quasars, we can actually see how galaxies evolve and how these central black holes continue on. And most of the emission that will come out of these as they're starting to collide and form will largely be in the infrared. That's where the next slide comes in. So in order to see this is basically for the range that a lot of these a lot of this information happens at the very base of the optical, all the way through the near and the mid infrared, and then out into the far infrared. And so we have, in terms of what we can use, we have infrared cameras and spectrographs. We had Hubble that would do from ultraviolet through optical and then a little bit into the infrared. We had Spitzer that would do from like the mid infrared, from the near infrared down, but then we needed something kind of in between that would cover that would run the whole gamut and have the increased resolution that James Webb does. And you can see the honeycomb mirrors again. And so what that'll allow us to do is, with resolution of 600 to 2400, basically the JWST will be able to detect things with line fluxes, basically at signal to noise, basically 1 part in 10,000, to where all the JWST instruments are actually going to be several orders of magnitude more sensitive than SOFIA, than the VLT, than Keck, than the Gemini telescope, and then Spitzer is, because it was relatively small. And because you have much more sensitivity, you can notice more things about galactic mergers and black hole collisions and other things that you'll be able, because the emission is not very strong, but it's still there. But if you have the sensitivity to pick it up, you can pick up very much fainter signals. And that's what we anticipate that James Webb will be able to produce. So it should give us 1 to 2 orders of magnitude in the sensitivity in infrared wavelengths, which will give us more opportunity to see things, like in this case, an early stage merger, where if I'm looking at things in the ultraviolet, looking at things in the red, you've got carbon dioxide or carbon monoxide that's moving with sort of a redshift of 200 to 400 kilometers, 200 to 400 kilometers a second. The blue is blue shifted to where it's now moving toward me with 200 to 400. So I'm seeing this spiral around, and then I'm seeing essentially the hydrogen region in there. So I'm getting more detail of what's going on during this initial merger. Is this an active galactic nucleus that's now essentially merging, and this becoming essentially dust lanes on either side? And so there's two different JWST programs that will observe nuclei. One is by Lee Armis, the other one is by Vivian Yu, and we're going to look at galaxy mergers in the near and mid-infrared, and then galaxy mergers specifically in the mid-infrared to figure out what causes the active galactic nuclei and what causes the black holes. The rest of this, the last 4 slides are all things to go check out. If you're interested in what we've talked about in the slides, they actually have a very nice website with various science demos and science projects that you can find at webbtelescope.org. NASA's Universe of Learning has a number of view space videos and micro observatory photos that you can actually look at, and some different program models and different projects that you can give to students, and find other subject matter experts in the area for Webb stuff. View Space has a number of videos in terms of seeing everything in infrared and what exactly Webb will be able to do. The micro observatory is kind of an astrophoto challenge that allows you to share some of your favorite astrophotographs. These are at Universe of Learning. And then the last one, there at the time of the training, which was in August, there were about 500 official events supporting Webb with multimedia material. So a lot of those you can actually find at other Universe of Learning events you can find at these websites. I encourage you all to go check those out, because there are plenty of NASA professionals outside of myself that are always willing to share more information and can often go into more detail than I did here. And the last thing I want to do, and it's about 2 minutes long, and I want to take a chance to promote the stuff that is going on at the college. We were just awarded a NASA space grant, Oregon NASA Space Grant Faculty Research Award that will allow myself, Dr. Mike Springer, who's our chemistry instructor, and my research collaborator, Crystal Hopper, and several students to work on various research projects, including mapping the Earth's interplanetary environment from pickup ions, searching for micrometeorites, searching for unidentified near-Earth asteroids. And we'll also have the chemistry students designing new liquid crystals with solar cell properties. So we're basically designing new liquid crystal molecules to have flexible solar cells for future space applications. All of that stuff is currently going on at the college. We have our annual art exhibit, which should be displayed early in the coming year in the new science and in the new health and science building, which we always encourage you to come check out. We always like to have as many students as possible. So of course, with the last slide, I have to put in my shameless plug. I can always use engineering or physics students. So if you know anyone that is interested in either of those programs, have them come see me. And we'll show the video because I can. I assume it'll behave. There it goes. It didn't want to behave. So I was going to play the commercial, but the commercial is on the commercial's on YouTube for Southwestern's YouTube page. There's a 2-minute commercial that'll talk about all the stuff we do in the physics and engineering department, and talk a little bit about the new building. YouTube doesn't want to cooperate with me, so we'll spare you having to hear any more of my voice than we need to. But
I actually have a couple questions if I could.
Okay.
You talked about at the beginning that well, first of all, there was a delay, but that also that they have a month window to launch. What is the delay? Is the delay a weather thing? Is it a mechanical thing? Is it?
It's more of a weather. It's usually a weather thing, and it's
Okay.
it has to do with weather, and then it also has to do with making sure that there are certain just launch conditions that need to be met. So there have to be certain certain levels of monitoring outside of the launch area, because there's even if you're launching from a relatively small area, you still have, because the rocket leaves at such speed, you have to, like, when they launch a typical NASA mission from Florida, they have to have like weather monitors from basically all up the East Coast and then all through most of the Gulf of Mexico, just to make sure that at no point during the launch that it's gonna run into a potential weather hazard, which is why it's sometimes tricky to get those launch dates to work the first time.
Sure. And then another thing you mentioned is that you talked about how eventually when this is up and running, people can request images or certain things, photos taken of things, I guess.
Right.
Who gets dibs on that? I mean,
those are basically every year NASA puts out what are called calls for proposals for various observing programs for various for various satellites and other instrumentation. So you'll have teams of astronomers and scientists that will, if they're doing a study on a particular type of object, and they have particular candidate objects that are in mind, they'll put in a proposal about a year ahead of time for if we were granted, say, 2 days worth of JWST time, we would want to take images in this wavelength at this resolution of this particular object and point the telescope here. And then there is a highly competitive proposal process that about 10%, I think, of those proposals actually get accepted. And then you get your telescope time and you get to take your data. And then it usually takes you about 2 to 3 years to analyze your data after you've gotten your telescope time. But you have to propose like a year to a year and a half in advance to get your telescope time. And as I said, it's a highly competitive thing. They did the same thing for Hubble. So whenever you see the cool Hubble images, that means somebody actually wanted to take that about 3 years before they actually did. But a lot of the images will later then be, once the data is taken, because NASA has a policy on public availability of data. Once the images are taken after the embargo period is over with, so that the scientists that propose to do the work can have a little bit of time, at least with their data, to work on it. All of the images should eventually be publicly available. So we'll be able to see whatever anybody else wanted to take pictures of. But in terms of how to get on that list, in terms of what pictures do we take, it's about 2.5 year process to get your proposal right and then get it reviewed. And it goes through a peer review process that usually has about 15 or 20 scientists that are reviewing it.
So you can't just take a casual snapshot, is what you're saying.
We'd love to be able to do that, but no, for some reason they don't want to put a multi-billion-dollar space telescope in the hands of rank amateurs. I haven't figured this out yet.
Oh,
I wish they would, because I'm very much a rank amateur with a camera. I'd love to do it, but unfortunately.
no. Oh wow. One of these years, right?
Yeah, exactly.
All right. Well, thank you very much. I mean, I always walk away from these things feeling smarter and yet dumber at the same time. So
I want to